a bit loud. So welcome to this lecture. Today we're switching languages. So we're going from Python to Fortran, and I would emphasize that I'm doing modern Fortran. So we are not going to go into Fortran 77 unless there is a reason for backwards compatibility or something like that. But so mostly it will be modern Fortran. And Fortran is a language with a really long history. So you probably have so it's already from 1954. So it has a long history, and it's one of the first languages actually were standardized as of international standard. So Fortran 66 is a standard, Fortran 77 is a standard. And so Fortran 77 was a very long version, had a long history, and there is a lot of software written in that because there was kind of no successor in many years. And there was a big leap in the 90s here with Fortran 90. But it was complete. The first version was actually mostly compatible with Fortran 77. So you could compile your Fortran 77 code with, and it would compile and work. There was an effort after Fortran 90 to create something called the F language, which the idea with that was to remove all the backwards compatibility from Fortran 77 and remove the legacy functions. Didn't work out, so that was discontinued. Fortran 95 was a minor update from Fortran 90. Then there have been major updates for Fortran 2003, Fortran 2008, and there is actually, I messed up my slides here. So Fortran 2018 is available as well. And the later versions here coming from 2008 also has object-oriented programming now. So all the class concept is there, everything is, so it has most of the features of other modern languages. And coming versions after Fortran 2018 will actually also introduce templating and generic programming into the language. So Fortran is still an active language being developed. There's a standardization committee that works. It's not as large as C++, but it's still worked on continuously. It's also going up on the programming charts I saw recently. So it's nice to see. So just to compare the languages here. So I have taken a Pascal program here just to compare the development of Fortran over the years and also compare it to other languages. So in Pascal, you can define a program, you can define functions, you have the begin and end constructs, if statements. Very modern language is also explicit that you have to declare everything in the beginning. So here, this is variable declarations. It's always done in the beginning of a program or beginning of a function. You can't mix them. Then we have C. Similar, instead of begin end, you have curly brackets. You can declare variables any place in the code. So it's similar to Pascal, but a bit more compact in its notation. So if we start with the same program here, but going Fortran 0. So the first Fortran that was not a standard, but was introduced. And the name comes from formula translator. So it was idea to be able to translate mathematical formula into expression that you could calculate without doing assembler code. So if we go to Fortran 0, it looks something like this. So you have these odd things here with 3, 8, 11. That is actually row numbers that you have to specify. You also have this, I will get back to that, this indentation here. So this is a row number, so that is uninteresting. But then you have a single row here, space, and then you have the row numbers that you can specify here, and then there are some other important columns. So it's organized in column-wise here. It's called fixed formatting, and that is because it was written on punch cards. It has to be a certain way to work. So these are row numbers for the do loop. So and you can define a loop variable here. But the most innovative part was this here. So this enables you to write computational expressions in very readable forms. You have also if statements here, which the 8 is when it's true and 4 is when it's false. So it goes to 8 if it's true, and it's that one here. Otherwise, it goes to 4 here, and you can see you have go to, and the 999 here is you have go to statement as well to move the code and stop. So it's very unsophisticated code. Let's see. Fortran 1, you got the ability to define functions. You can specify formatting commands here. So that is how you should output on the screen or the terminal, similar to what you have in Python with the formatting statements. What to do more? That was most formatting. You also had a continue here, a keyword for the do statements here. You can do continue. You just still have to specify the line number here, 10, at that point. Then we have Fortran 4. We got a do. Let's see, not too much more here. And most of it happened in the next one here. Isn't it the same? Okay, Fortran 7.7 here, things happen. So here you have if, else, and if. You don't have to specify row number for if statements anymore. You also have the do statements again here, we continue here. You can declare, why isn't that updating? I'm going to switch here because it doesn't work. Sorry. Percent of view was not very good. So let's skip this one here. So this should be 47. And then we have if then else. And then we have the major update here in Fortran 1995. So here you can see you have, you can declare, there's no line numbers anymore. You have free format here, so you can actually place the code anywhere on the line. You declare variables here. There's also a way of declaring the precision here, which you can select here from this one. You can have subroutines in your code like this. You also, So this is kind of a free form Fortran, which is very similar to Pascal in that sense that you can have begin, end, and all those features here. Is it moving?
They put a dot on your.
Yeah, I know. It's just want to have the ability to move from slide to slide. Okay, so yeah, I was part. Yeah, so source form. So as I said before, modern Fortran as Fortran 90 and above can have two different source forms. So you have free form. That is, you can have max 132 characters per row. This is usually not enforced by the compilers anymore, but this is according to the standard. So if you write lines that are more than 132, you're out of the standard definition. You can have comments here anywhere on the line. You can have an and sign at the end of the line to continue to the next line. You can have multiple statements on a line separated by semicolon. So if you want normal things, you have one statement per line, but you can have multiple using the semicolon. In the fixed form, which is also supported by Fortran, modern Fortran, you have code in position 7 to 72. You have line numbers from 2 to 5. You have comments here in position 1 of the file. And you can also have continuation by putting any character on column 6 and only one statement per row. This is a typical Fortran program. Here you can see here that you have a comment you can put after a line. You can have and here to continue to the next line. And you can place any code wherever you want in this form here. And you can also have inside a program, you can have subroutines here. So this is the subroutine. And you can have that in a contain section here. I will go through this more in detail later on. You can also have declarations like this that you don't have to specify the dimensions when you are calling the subroutine. Program structure of a program is defined by starting with a program. You can give it a name. Then you have specification statements and executable statements. So it's not like C and Python where you can declare a variable whatever in your code. You have to declare your variables in the beginning of the program, in the beginning of the subroutine, the beginning of the function, and then you can use the variables. And the program can have, so here you have the variables, the statements, and then you have a contains part here, which is optional, where you can have internal subroutines inside your main program. And then you have end here to end the program. And the only thing that is required in any main program of Fortran is the end statement. So all other stuff here is optional. So the smallest Fortran program you can write is a single end statement. So Fortran is not a script language. So it's a compiled language. That is, it translates all your source code into object files or binary code, which is then executed by the processors in one go, which is different from Python, where you translate one row at a time. So program in an operator is executable code, is machine code, a chunk of machine code in a file. And inside that file, there is links to the system libraries for interacting with the operating system, the file system. It can also have links to external libraries as well, math libraries and so on, that you compile yourself or have been provided on, for example, Cosmos. There is a standard libraries installed. So how do you create a program? Yeah, hand coding machine code is not something you do today anymore. So the next step up of that is writing in assembler source code. That is a bit higher level, where you, instead of putting the numbers in for the instructions, you put pseudocodes for each operation, which is also a bit less hard and really hard. So you also have, you can use a high-level language like Fortran or C that translates the source code to binary machine code easier. Then you have Python, where you compile and execute each line. There is no distinct compile and link step. You just execute the code from the command line or from a source code file. So the step of making executable here is you write source code and you compile your source code to object files, which is unlinked machine code. So there are objects which have a machine code with links to other things that has not yet been established. And then in the final step, you link your object files and libraries to an executable. So it's a three-step process to write. So write the source code, compile, and link. And in many cases, you can do these two in a single step as well. But this is a model here. So you have your source code file here, usually .f90, for example. You compile them, you get the same file name here, but the .o extension. You have a source file here again, object file, and you have multiple of them. And you have libraries here, which also are pre-compiled machine code. And then the linker puts all these together here, finds the links between them, and creates an executable, which you can run on the command line. So, for example, on Cosmos or a Linux machine, so here you can see you can load the FOSS module here. You should change that to the latest version, but if you load the FOSS, it's free open source software. So that is a tool chain that provides the GCC compilers that we need for compiling. So the GCC compiler which we use in this core is called Fortran, and that is a compiler that we use. If you type Fortran here and version, it will show you the version number. And I think if you load the latest one, I think we are 11 something in the version number now. So if you want to compile Fortran, you can write source code, use the F90 as an extension, and then you can compile the Fortran source code to an object file using Fortran-C, that's for compile. You give it the source code file name, and that generates my source.o. And you can also give multiple source code file by just adding them together on the command line, and then you get source1, source2.o. Linking is done by just saying Fortran and then giving you all your object files. That by default generates an a.out file. But usually you want to have a name of your executable, so you do object files here, and then -o myexec. So your binary executable will be called myexec. And that generates an executable that you can run on the command line. But you can also, the nice thing with the Fortran compiler is that you can actually do everything in one single step as well. So you can give your source code files like this, -o myexec, it will compile and link everything together. So it's a bit easier than the other compilers in that sense. And you can have multiple source code files here as well, and then it will compile together. The only thing you have to look out for a bit here, if you have modules which you come into later on, that you need to, if a module is used by another module, it has to be compiled before the other ones, if you give it on the command line here. So I'm thinking I'm going to show you how it can be done. So I have installed the Fortran compiler here, so you can type Fortran -version here. And you can see here I have 11.2 here. So now I'm going to do just open an editor here. We set it up on my other screen here. I think I'm going to do it like this instead here. So let's see here, just do a file new. So I just type here program my first print star, which is a standard command for printing here. Hello, Fortran. And program first. Then we save this here as a we call it my first.f. So you can see here I have a my first here. And now I can do Fortran. My first. And then my first here as well. So I give it. So this I will compile the my first and then output it to an executable called my first. And no compilation errors. So let's see what we have here. My first. So this is on a Windows machine, so I get my first.exe. But if you run this on a Linux machine, you will get my first. And if I just type my first here, it will just print out Fortran here. So now we have an executable file. So this is a completely standalone machine code file that contains everything to run it on my machine. So let's go to the language itself. So variables, important part of any code. In Fortran, you can variables are named. They can be a maximum of 31 characters. They can contain letters, numbers, and underscore. You can have both uppercase and lowercase characters, but they are case insensitive. So Python is case sensitive, Fortran is not. So variable my first is the same as my first uppercase. So there's no difference there. Also, the first character can't be a number. So variables must always start with alphanumeric character. So valid variable nums are A underscore thing, X1, mass, Q123, time of flight. This is not valid. This is not valid because you have a space. Underscore is a non-alphanumeric character, so you can't start with that either. But this is okay. And if you have some older code like Fortran 7.7, you usually have the limit of 6 characters. So Fortran 90 increased the size of variable names to 31 characters. The built-in types are integer, real, complex, logical, and character. So these are the basic data types that you build upon. So you can see already here that it's a language that was done for computing. You have complex numbers here as well. And you will also see that character here and strings are not the strong side of Fortran. Declaration, you first give it a type. So Fortran is a type language. You have to declare all your types. There is a misconception that you don't have to declare a type. That comes from its inheritance to Fortran 7.7, which have implicit type rule, which gave it variables that started with I to kn, I think, was integer. All other variables were floating point, but still everything was typed. And I will teach that you need to declare types in Fortran here. So you give it a type name, integer, real. You can specify multiple attributes that control the variable type. Then you have a double colon and an entity and a list of variables here of that type. Here you can see I can declare integer colon A. So that declares an integer variable A, real colon and then the name. Logical, which is a Boolean variable, also with colon. Arrays can be declared by specifying the name and a bracket or parenthesis here and the size. So this is a fixed static array. And then you can declare a two-dimension here by just doing k20 by 20. There is also a way of declaring it using attributes instead. So you can put the size of the variable on the left side here of the column. Then all the variables you declare here will have the same dimension here. Characters, declare this is a single character variable. If you want to have an array of characters, you can do dimension 60 here. And that is not the same thing as having a string of 60 characters. That is an array of characters, so you can't use it as a string. You can have a string that is 80 characters long by specifying character parenthesis len 80 and then declaring it here. Then that is a string. Then you can have an array of strings. So here you have character len 80, line 60. That means that you have 60 strings for the size 80 here. And all strings in Fortran are fixed size. So there is no dynamic strings like you have in Python. Yeah.
Why would the array of characters not be a string? Wouldn't the position in memory wouldn't it be consecutive?
Yeah, yeah, they will be consecutive, but you can't work with strings in Fortran using an array of characters. So they're laid out the same in memory, but you can't use the string functions on them. So
there are no pointers in Fortran?
No. Yeah,
I guess you have implicit pointers,
but it's not as easy as in C you have this equivalence of pointers and arrays.
Yeah,
there is no such equivalence here, and it's very hard to go from a character array to a string. So, like I said, this is a it's not a character; it's a string that you can use to assign using the string quotes. But you can't assign, for example, an array of characters with string operations. So there is a distinction. I mean, in memory they are the same, but from language perspective, you can't mix them.
Yeah, in C you just go to point of position. Yeah, you just wherever you want to.
Yeah. You can probably do some kind of cast, but it's harder to do this kind of casting in Fortran than in C. You can also declare that something should be a constant by adding the attribute parameter. So then A here will be a constant variable that can't change during execution. And you can use those constants to declare other variables as well. Then there's also additional parameters for declaring the precision of the data types. And here is where it becomes a bit complicated with Fortran, because precision specifier is dependent on the compiler and the system architecture. So by specifying a number here, it's not guaranteed that it's the same from every system. So to solve that, Fortran, the compiler have added a special function called selected real kind and selected in kind to declare constants that you can use for declaring variables that will be the same on every system. So, for example, I have been told by Joachim here that not show this too much, because so you can declare a variable real here with a specific precision specifier here. In this case, it's 8. And you can also do 4 here. And usually on Intel-based system, that means that these are 8 bytes floating point. And this is 4 bytes floating point. But it's not guaranteed to be the same on all systems. And you should avoid using these kind of declarations in your code. What you should do instead is create a constant here where you specify the precision here that you want to have 15 decimal points and 300 exponent size here. And then you will get a number here, which is assigned to a constant. And then you can use that constant here to declare your floating point numbers. So significant decimals, and then you have This is can represent numbers from 10 to minus 300 and 10 to 300. And you can also specify one problem you have with this here, that you can, the Fortran is designed, it has a lot of legacy, you will probably, and because it, at the time we designed the language, storage was scarce. So variables, scalar values that you put in your code will be represented with the least amount of bytes as it can by default. So if you put, for example, 6.2 without this extra string here, it will be represented as a real 4 byte floating point, unless you add this suffix here, which comes from this, it should be AP here. Then the scalar will be represented with the same precision as you have computed here with this selected real count function. So one example here I usually show is that you can, if you assign pi as a constant or assign a value to pi 1 and pi 2, and you give one of those here without this suffix and one with the suffix, and you print it out, you can see here that they start to differ here after 5 decimals here. Then it kind of becomes different. And that's because this first scalar here will be translated to a real 4. And this one will be translated to the precision you specify here. So by default, you would have less precision. And that is something, in some compilers, you can say that all real should be real 8 when you compile. But by default, it will not do that. So you can, if you have problems with your precision in your iterations, or it could be that you have missed some of these things when you wrote the code, that the scalar is not represented or stored in the binary with full precision. I touched upon it before. So there is something called general type rule, which is if you don't specify anything in Fortran code, so variables starting with I to n are integer, and other variables are real by default. And this rule has led to many problems and bugs and should be avoided in modern Fortran. You should always place a directive called implicit none in every source code file that you write, because that forces you, or says the compiler, you have to declare every variable explicitly. It ignores the type rule if you put that in. So usually have that in your main program file and also in your modules later on. You assign variables using the equal operator. So real R key, you specify this suffix here. You can have the same here for integer precision here. So you have a suffix for that as well. Logical variables, .false, .true. And characters are with single quotes or double quotes. And you can do the same thing with Python here. If you want a single quote, you can start with a double quote and so on. Another thing that is important to realize also, that the variable that you declare in Fortran, until you assign it a value, it's considered undefined. So you should never use a variable that haven't assigned, because it can point to somewhere in memory. And it is not necessarily 0. It can be something just garbage. So, for example, if I declare real speed here, when it's declared, the variable exists, but it's undefined. And you should never reference those. And when you assign it here, speed 42, now it's defined and you can use it again. And also, same thing applies to arrays. So if you have defined, declared an array, if you haven't filled it with data, even if you just filled one of them, it's considered undefined. So array is defined when all elements have assigned values. There is also another data type you can use in Fortran. It's called derived data types. And derived data types is a way of declaring your own data types that can contain a mix of different data types to produce another a data type that you can use like any other type in Fortran. So you define them using a type statement block, and then you can declare them using type, and then the name of your data type, and then the variable. So for example, here I have a particle here, type particle, and then I have 4 fields here, X, Y, Z, and M. I have a module here that contains my precision, the constants here. So this is a double precision constant that I have declared in my module here, n-type particle. Then you can declare an instance of a particle using type particle P. So now you can use P as any other variable in Fortran, and you can assign it using, and this is also a bit, so the dot, in any other language you use the dot as to get to the attributes, but in Fortran you use the percentage sign, which is confusing because in other languages it's a modular operator. So P %x here equals to 0, and you can access the different fields in your own data type like this and assign them. And you can have mixed data types as you don't have to have a single data type, you can have multiple data types inside a single data record. And then you have to, of course, assign them with different values here as well. Operators. So these are the common operators in Fortran. You have 2 stars, that's power 2, multiplication, division, addition, and subtraction. The order is also in that order here. Parentheses are processed first, then you have operations with double star, operations with multiplication and division, plus and minus. Also, you have relational operators, and you have 2 types here. So on the left side are the modern relational operators. On the right side here are the ones that are compatible with Fortran 77. So, and reason for this is that Fortran 77, it could only use a limited set of ASCII characters, so with 7-bit characters. So that's why you have this shorter, that couldn't use these special characters. So that less than became LT, and less than equal to, and so on. Most of these are the same as for in Python, except for the not equal, which is a slash equal instead of exclamation equal to. So this is the only difference here. Logical operators, you see here, you have dot and, dot or, dot not, dot. And here you can't use and or not, you have to have the dot around your operators. Also, divisions will be truncated towards 0 if you have integer divisions here. So this is the same 2 plus minus 2. Yeah, and some here that some of these will truncate here if you have integer expressions here. So this is equal to this one here, which is 0. If you mix data types and expressions, but Fortran will convert the weaker of the types to the stronger type. So in this case here, you have real integer, so a times I. So I here will be coerced to a real data type. So this will be a real expression here, which will assign to B.
B was integer.
Sorry?
What happens if B was an integer? Now you declare B as a real, but integer according to B. You would get a real from A times I, but we would be able to store it in B.
Yeah, that's why, because the result, because in this case, I want to have a real result.
Yeah.
And in this case, this will be, I will be real in this expression.
But if the variable you want to store in, if that was declared an integer, so your right hand side would be real when you are real and an integer.
Yeah.
But would you be able to store a real in an integer? Would it be cool?
I think you need to do a conversion.
Okay.
Yeah. I think going from other way around is difficult. Then you have to have you can put int before in parentheses to do the conversion. But then it will first be this will be a real and then converted to integer.
So would like a real times complex or or integer times complex then be coerced to complex?
I haven't tried. I think so, but I'm not sure if you could. Yeah, you could probably multiply them and you get the complexes. But I need to check. Array expressions. So all of these operations operators will also apply to arrays. So if you have arrays of the same type, you can multiply an array with a scalar value, and then that scalar value will be broadcasted array and operated on. So if you multiply by a scalar, that value will be multiplied on all the scalars in the array. And also, if you have two arrays of the same size and multiply, it will be do element-wise multiplication of the arrays. Also, the order of the operations is not specified in the standard, and that's the idea that the compiler should be able to do the most efficient implementation of this. So hopefully we'll use some kind of math libraries behind the scenes to make it really efficient. Here you can see here I have a two-dimensional array here, 10 by 20, A and B. I have a single vector here with 5 elements. And this operator here will be this operation of Aij, Bij, and it will return an array of the same shape. The thing is that to be able to do these operations, you need to have an array of the same size to assign to. So you have to declare all variables. You have to have a C here, for example, 10 by 20 that you assign this operator to. This here will be V plus 1. So 1 will be added to each element of the V array. Here you have 5 divided by V, that is a 5-element array. And here I extract 1 to 5. So the rows here. So this will also be a one-dimensional array with 5 elements. So you can see here you can have the same syntax as in Python to do array computation. So this will be a one-dimensional array, the result of this operation here, and then you can add it to 5 divided by V. You can also do comparison here between arrays. So A dot equal dot B, that will be true if all elements are the same in A and B. So we go into arrays and matrices.
A quick question.
Yeah.
So if you have 2 arrays which are the same size,
yeah,
and you do A equals B, like can I assign to an array?
So that operation will be just return true or false.
Okay.
So if you do the comparison, it will loop over and check if they're the same and return true or false. So that will not return another array.
It's not going to return another array which has like true, false, true, false, true, false. Like
no, it can't.
Not element wise. It's a reduction over the false.
Yeah, but they will compare the values regardless of true or false.
Yeah.
But it's kind of comparing two floating point arrays is always tricky.
Yeah.
But if you have integer arrays, that will work better. We always touch about arrays. So it's arrays are kind of the bread and butter of any Fortran application. That is you do array computation, and you can do them. You can allocate them statically, which we have done as I showed before, or you can do them dynamically. And as I said, it supports both indexing and advanced slicing and assignment. Also, Fortran arrays are 1-based by default. So they start with 1, not 0, which is important to remember when you communicate with Python, or C for that matter. You can redefine the indexing, but by default, they are 1. So as I said, you can define here an array that goes from -3 to 3 here using this notation here. So instead of just specifying the size here, you can specify the index here as well. Assignment of an array is given by row and column, and then the number. But you can also do this if you have a two-dimensional array. k equals to 5. That will assign all elements of the array to 5. So there's a lot of, you don't have to do a lot of looping in Fortran to do things like this. You can do it automatically. Here you have a one-dimensional array with 5 elements, and you can assign them here using this notation here. So parenthesis slash, and then you list the elements, the values that you want to assign, and then slash parenthesis. And you should perhaps have the suffix here as well behind these scalars here to be completely correct. But this is a way of assigning multiple values to an array at the same time. You can do slicing. So here I have an array that is 4 by 4, and have a real here that is B4, and a C here that is 4 elements, so one-dimensional arrays. And I can assign B here, the first row here and all columns. So the second row, all columns, is assigned to B. Then I have A, column 1, all rows assigned to C. So this is very similar to what you do with array notation in Python.
So the copy. What happens if I change B or C? Do I change A as well?
No, it's copying.
It's copy.
So by default, Fortran, those are always copying. And you can also use the combination here. You can assign row 5 here with this notation here, parenthesis slash and then the values. Yeah, the same thing here. And also the arrays are stored, that's just like I said before in Python, arrays are always one-dimensional in memory. So the dimensions here is just a way of jumping through the arrays in a way that it's easier to comprehend the data. And they're stored column-wise, which is not the same as in C or in Python. So if you have a real array, you can see you have 16 elements here. And if you have an array that is 8 by 2, they are stored column-wise. So the first column, second column. And 2 by 8, still column-wise here like this in memory. And that's important when you later on communicate with Python. You need to tell Python to create arrays that are column-wise allocated. Otherwise, they are kind of turned around when you pass them over. But they are stored like this in memory all the time. So they're just one continuous block of memory, but interpreted in different dimensions. Is there one we did in this one? You can also have arrays of derived data types. So in this case, you have a data record here. I can declare an array of 5 records like this. So it works the same thing, just like any other data type can be used as an array. Then you have the loop over here and the I percentage and then the field of the array. Conditional statements. We start with the if statement. The simplest one, if parenthesis, and then you have a logical expression here. If that is true, the statement is executed. You have if expression, then, and then you have a code block here, and if. And then you can nest them like this: if, then block 1, else if, then block 2, else, and so on. So similar to Python, except that you need to have parentheses of the expressions. So here you can see here, if x greater than 1, then execute that one. If it's less one, this one. And then you can have if flag here. So you can have Boolean variables here. Then you just have to do if flag, then do something. Otherwise, do something else. Here you can also see here, I start all my program with implicit none. That forces me to declare all variables I have in my code. Then there is also something called a select statement. And that is if you have a lot of conditions you want to test, the if statement can be a bit cumbersome to work with. So select case expression here. That is the expression that you want to evaluate on. And then the selector here is one of the alternatives coming from the expression here. So if that is true, this will execute. Then you can list them multiple of these. And then you can also have, if none of the case statements is fulfilled, this will be executed here, case default. Here an example here, select case value. This is what I want to evaluate on. Then you can test different here. So greater than 1, for example, equal to 1, between 2 and 9, 10, 11 to 41, and so on. And if none of these are fulfilled, it will go to the case default. Repetitive statement. So that is also a common way you want to implement things, be able to repeat things in different ways. And I showed you before we have a do statement. You have a do and a loop variable, and then you tell it start value, end value. Then you loop here. Then you can have start value, end value, and a step. And then it just jumps with a certain step length here. One important thing is that the loop variable is not allowed to be changed to current standard. So you can't change I inside the loop here. It must be unchanged.
This is inclusive. The end value is included.
Yes.
As opposed to Python where it's excluded.
I'm not sure if you put something that is, or it could be that it skips the end value.
Yeah, but 1 through 10, that actually gives you 10 values.
Yes.
Python, that will give you 9.
Yes.
Yeah.
Yeah, that's the correct. Python does it a bit odd, and here is more explicit. Then you can control the loop, the do statement as well. So you can do exit that continues after the end do statement here, and then you have cycle to go to the next iteration as well. I would try to avoid using a lot of these here because the code can be quite unreadable at some point. Yeah. You can also do a do statement with a condition. So do while a certain expression is fulfilled, then execute a block here. So for example, if x do while x less than 1.05, compute here, this will execute until x is less than, it executes when x is less than 1.05. So that will produce this output here. Can we take 10 minutes break? Or you want to?
Last line, that's 1.1, that's larger than.
Yeah, because it adds here. No, it's so strange.
It makes sense for a repeat until.
It adds here. So it's
okay,
here,
yeah.
and then adds here, and then it prints out, and then it exits. So let's do a 10 minutes break, and then. Okay, so do while. Built-in function. So there is a runtime library in Fortran as well. It's not super extensive as in Python, but it's still there. Of course, you have the mathematical functions. Doesn't have to explain that too much. What is interesting, all these functions work on arrays as well by default. So if you call sinus on an array, it will compute sine on all the elements in an array. You have conversion functions here for converting apps, truncate a floating point, converting a floating point to an integer, rounds a floating point to the nearest integer, real, converts an integer, floating point, and so on. You also have max function that returns max of a certain number of elements, min at the same time. You have some matrix and vector functions, so dot product, scalar product of you times V. We have matrix multiplications with matmul. So it does the matrix multiplication. So the normal multiplication operator is element-wise. If you want a matrix multiplication, you have to use the built-in matmul function. You also have a transpose C, which will return the transponent of the matrix. Yeah, so here we have three arrays here. So this will be a element-wise division between the elements in A and B, which will be assigned to C. And then you can do square root of A that will assign C the elements of A square root. So it's very similar. You can do in NumPy, but it's directly in the language. So I want just to show a bit bigger example here. So I have so this is for my field mechanics, so stiffness matrix. And the idea is to compute an element stiffness matrix here, which is done using this expression. So transpose of G times K element and then times J. And I can see I have a G matrix that is 2 by 6. I have a element matrix here that is EA times L, and then very simple array. And the length and the constants here are computed like this. Yep.
Did I miss it? Was there a built-in cross product, or is that what?
There is no cross product.
Okay.
I could have. I don't think so.
Okay. Oh.
I'm not sure. There is very limited amount of matrix functions. So.
Okay.
So here is an example how I can implement this. So I declared all my variables here that's used in the expressions. I declared KLL 2 by 2, KA 6 by 6, and G 2 by 6. And I assign them here. I use also a selected real count here to make sure that I get the right precision of my variables. I use the suffix here to declare all my scalar constants here. I compute the length here. I compute nx, ny, and nz. And then I assign my arrays here row-wise here. So row 1 colon equals to 1 and minus 1. And then row number 2, 1, minus 1 and 1. And then I just do KEL equals to KEL times EA divided by L. So that will compute the local array. Then I assign my J's here, 1, and then the values here, and 2, like this. So I can see the shape here. And then you have to, of course, it's much easier to do a nice expression in Python here, but you can see here, I start from the inner here, I have transpose G times KAL, matmul this expression times J, and I have to nest them like this to do the matrix multiplication. And then I print them out like this. But this is, so you can do a lot of things in a single row here using the matmul expression and combine that with transpose. So I don't have to compute that as a simple variable. I can just do transpose times KEL, and then the matmul here is outer one here. Yeah, it looks like that if it's correct.
There was something interesting. If you go back one slide, is this in the print statement? Is this like a sort of list comprehension at the end?
Yes, actually.
Yeah.
I will come to those shortly, but the thing is, so the first parameter here, that is just standard output.
Yeah.
And this is the formatting here. So this says 6 floating point numbers with 10 decimals and 10 width and 3 decimals. And then I use K-I-J. So J is the list comprehension here, and that will just loop over here and print out K-A and vary the J here.
I see.
What does the G do?
So G is the in loop, so it loops from 1 to 6.
No,
So,
not the J, the G, the 6G.
okay, so 6 is the number of numbers to print.
Mm-hmm.
And this is the format. So J is a general floating point format.
Okay,
And then with
Oh,
10
general.
and so it's the same as in Python. And then you have to do like it's really strange. You have to have a stuff here in parentheses and then inside a string here. There's a lot of inheritance from old times in this language. That's why this is something that has been around since Fortran 77 as well. So now, how do you organize your programs in Fortran? So in Fortran, you only have one main program, and that is declared, as I said before, with a program, end program. That is your main program. That is the starting point of the application. The end statement is actually the end instruction that terminates the program execution. And you can only have one main program. So you can't have multiple source files with program statements. You can stop execution using a stop statement. That can be used in any program unit. And you should kind of document if you use stop statements in your libraries, because stop will stop any program, regardless of anything. You can have stop code here to provide some numbers output from the stop statement, but you should try to avoid having in your own library, because it is not. It's better to return from a subroutine with an arrow code and then stop your program, because if you call a library that does a stop, it will stop your program as well. So not ideal, but it's one way of stopping your code execution. Subroutines, also functions, but there are three types. You can have external subroutines. Those are placed in separate source files, have an implicit interface, and they can be implemented in other languages. So basically, you compile a subroutine as a separate source code file, produce an object file which you link into your code, and then the linker tries to solve any calls that are not outstanding. Internal subroutines are contained inside program units. So it could be in your program and also in module subroutines or subroutines. And you can have module subroutines, which are subroutines placed in a specific module file. And I will come to what a module is as well. These are the three ones. These are the ones that are most likely to create errors and problems with calling, because you need to make sure that they are the same calling convention. So you have the same parameters in both in your code that calls and also in your subroutine, because there is no check done. So if the calling interface has the same number of arguments and you link it, and the subroutine has a different type, it will still call, but it will just interpret it as garbage. So there is no check being done if you use this kind of method here. It's just a linker checking if it can link or not. So subroutine, declare with subroutine, the name, and then you have a list of so-called dummy arguments. And that's why, because these are references to other variables that you call the subroutine. So in Fortran, all calls are done by reference. So if you put the variable in a call, it's the variable coming in here. There is no copying with that. So by default, it's by reference. So if you modify a variable inside a subroutine, it will modify it outside as well. You can change that, but by default, this is the way. And then you can return from a subroutine using the return statement. Yeah, as I said before, subroutine passed by reference, and arguments to subroutine refers to the actual variable in the calling code. You must redeclare your subroutine arguments inside a subroutine. And you call the subroutine using the call statement. Control can be returned by return. And you can have multiple return statements in a single subroutine as well. So this is a separately compiled subroutine. You have my subroutine, you have A, B, and C. And here you can see you call it with A, B, and C, and you have the variable declare here as well, but you also have to declare them here. And one thing that, in this case, you don't have to declare the second. So this is A here, can be used to declare things in the subroutine here. So for example, it could be the size of the arrays, and you can declare them here as a size here. And if you have a two-dimensional array, you don't have to declare the last dimension here, because that can be figured out by having the A here. And it will link this program. You can also change the actual variable types here, as long as the number is the same, you can call them, but that means also that you can have the problem that the real here is interpreted as an integer or so on. So this is one file and second file, and you compile it, and the linker checks to see if this call here can be linked to this subroutine. If it does, it links. It doesn't check any parameters, it just checks that it can link them. Function is similar to the subroutine, but you have the option here to specify a function to return. Same dummy list here, and then you assign the function name here to the return value. That means that is what you assign to the function as well. So you have a real function here, and then you f equals to sin x. That is the type of the function here, and that is what is assigned to y here. Modules. This is something what was introduced with modern Fortran 90. And it packages global data, so you can put variables here that should be available for constants to other modules. You can put derived data types and associated operations in here. Subprograms, interface blocks, name list definitions. And the idea is that you, like modules in Python, that you package everything associated with some kind of task. It could be a module for interval arithmetic. It could be a module for finite elements of a certain type. And so logical units of your code. So it's a way of modularizing your code, making it in more nice things that you can work with easier than having a large source code. Modules are implemented in separate source code files. And in your source code file, you start with module and the module name. And here you can have specification statements, that is, statements that declare global variables, global constants. You put them here. And here in the contain section, you put your module subprograms or subroutines that you want to expose to the ones using your module. So one way of using a module is to provide constants here for your precision. So you have integer precision here selected in kind, real kind selected real kind here, and I provide them as two parameters here in my module. Then if I want to use those constants in another source code, I just provide use constants. And use is the way you use a module in Python. That's similar to the import statement in Python. So use constants, and then here those constants are available to you for use. You can also have, so here in the first part here, you can declare your variables. You can actually add an attribute called private. If you don't want a variable to be exposed in your module to the user of the module, you just declare private here. And then it's not available to use it. And it's hard. So it's not in Python, there's always a way to accessing private things. In Fortran, there is no, it will not link. If you try to use a variable in a module that is declared as private, the linker will fail. So that could be a good way to doing as well. You can also do public and private on subroutines inside a module. So by default, all the subroutines here are public, but you can declare them as public or private in the starting here. So here you declare public bar2e. So I want to show this one here, but you can also do public bar2e or private bar2e, and then it will make sure that this subroutine can't be called by other programs that use this module, but it can be used internally in the contain section. So you can have internal method that's only supposed to be used inside the contain section. And here are examples of how my main program, I have my module here, use truss. And now, because truss contains a bar2e, I can do call this function here and use that. And all the variables and public data types are now available in my main program unit. Yeah, I was parameters of the cost per reference. So changing a parameter in a subroutine will affect the variable in the calling routine. And the reason for this is also legacy. It is quicker to call a subroutine with references. There's no copying being done. But you get undesired side effects instead. So if you don't know if a subroutine modifies your data, I had a problem. I had a code before. I found a library which was really nice at solving some things. And I put my variables inside here and it worked. I got something back. But in the same time, it actually also used my input variables as working arrays. So when I got back from the subroutine, everything in my old data structure was ruined because it's, oh, by the way, I've used your things here to solve other things. So then I had to actually copy things before I send it to subroutine because it's modified. So that is something so you have to really look at the documentation of modules in Fortran, what they do. Yeah, also the parameters, of course, doesn't have to have the same names as the calling routines. Loss dimension can be left out for arrays if you have separately called subroutines. So in this case, I have two source code files. I have, because this routine doesn't know about this code here, to call this, you have two arrays here and one vector here. I need to specify in my for here the sizes of the arrays that I want to compute. So A here, I add rows and columns. For V, I put elements. And then here in my declaration here, I can declare my A here, and I want it to be a one-dimensional array. I can do that. So A here is rows by columns. That is perfectly okay because it's the same size as A, and just a way of reinterpreting A as a one-dimensional array. And here I put elements here as well. So now I can do this vector operation because all the parameters are known. I can do this. A benefit of using modules is that you don't have to explicitly declare all these variables. As I said before, you have the explicit, implicit ones here, separately compile F9. The compile does not have all the information. But in Fortran 90 and later, if you declare your functions in subroutines or contain sections, the compiler has all the information to make the call without the size parameters. So it can help you out with that. And in this case, you can declare your arrays and vectors with colon, comma, colon as just the dimensions of your arrays. And it explicitly will give the compiler information to determine the sizes of your parameters. So you can have really short parameter lists. And you can actually also, like in Python, you can query the sizes of the arrays coming into the subroutines instead of having to pass them as parameters over. So if we, in this case here, let's see here now. And I have an old here. I can, of course, I can query the sizes here, but let's see what. Yeah. So I'm going to convert this routine here, which has rows and columns, to something that is in a module, and I only have to use A when I call. So now you see I have to pass along 20 by 30 here for a parameter, the sizes of the array. But if I instead put the routine in my module, I can declare A as colon, comma, colon. I can query here using size to get the size. I can do this A here directly without having the size information. And you can see you can call it with just my sub A. So the information about the size of the array is passed silently along here, and you don't have to explicitly pass it along here. That is handled by the compiler automatically. But that requires you to have the subroutines inside modules or inside the contain sections of your main program. Otherwise, the old rules apply. You have to explicitly call or implicitly call specify everything in your subroutines. And you can have it here, program in the contain section. That you can see this as a small mini module. So if you have small programs, you can put your subroutines here in this part of the code. And this is also called assumed shape arrays. You can get the same functionality if you have explicit interfaces, but then you have to tell the compiler what interface it should expect of this function here. So you declare an interface here and you tell, okay, sub4 has this kind of declaration. It uses assumed shaped arrays, and then the compiler can do the linking and expect that this routine is compiled separately, but it has this interface and it can do the linking, and you don't have to have modules. But my recommendation is to skip this, put it in modules, then you get that for free. Then you also have something called automatic variables in your subroutine. These are temporary variables that you can declare from sizes of parameters coming in. They're created on the stack and automatically allocate on the desired size, but they must be in the stack. The stack is a limited amount of memory that's really fast in the computer. And usually variables in subroutines are stored on the stack. So in Fortran here, you have, so my routine here is one parameter A, declare here, and then I can declare another variable B that takes the sizes of A and creates a two-dimensional array here of the same size as A. And this variable here is an automatic array because it takes the size of the incoming array, allocates a similar sized B array here that you can use in your code as a temporary variable or something that is similar to what the array sizes that comes in. So some array features here also. So one thing that came with modern Fortran was allocatable arrays. So up until now, we have had fixed size arrays only. But in many cases, you don't know the problem size at compile time. And then you need to be able to allocate arrays when you run your code. And so what you need to, when you do this, you have to always declare an array with the rank defined. So you have to decide if you have one-dimensional, two-dimensional, three-dimensional. And when you have defined that, you can allocate the actual size using an allocate statement. And before that, in Fortran 7.7, you have this kind of work arrays that was pre-allocated at compile time, which you didn't use as allocatable arrays. When you're done with your variable, then you can deallocate using deallocate. A new feature in recent Fortran standard is that if you have an allocatable array in a subroutine, you actually don't have to explicitly destroy it. When the call returns, it will be deallocated. But it's not a bad thing to explicitly deallocate. So the declaration is similar to what you have in static arrays. Instead of numbers here, you put colon for one-dimensional, two-dimensional colon. Then you add the attribute allocatable to your declaration. And then you declare variables just like normal. But before you use them, you need to allocate them. And that is done by the allocate command, which allocates the variable f here to 20 elements, and this to 20 by 20 elements. And when you're done using them, you can just deallocate them f and k. It's also possible to do it in a single statement like this, and also deallocate them in a single statement. One thing to be a bit careful about when using this is that if you have an iteration, for example, iterate over things, make sure that you always have a pair of these. So if you have iteration, if you allocate and you don't deallocate, you have the risk of filling the computer memory. And at some point it will stop and crash your program and perhaps also make the machine very non-responsive. Array subobjects, as we have touched upon it already, you can extract sub-objects from arrays that can be used as arguments to functions that need arrays. And you can use them as parameters of subroutines, very similar to the index notation of MATLAB. So here you can see I have declared an array 5 by 10, and I call write array, which is a subroutine here that writes an array. But you can also create a vector here by using this index notation here. That will generate array or vector that is passed over here. So the write vector function doesn't know about that this is a sub-array. And you can do a smaller size two-dimensional array here as well, by 1 to 5, 5 to 10. And that is the array sub-object that you pass over to the Fortran function here. And the write array here doesn't have to know about anything about that this is a sub-array. So in your subroutine, you can declare it as colon, comma, colon, and work with it just like normal. Yeah, you can also have the indexing doesn't have to be continuous here. So you can actually have A, 1 and 3, and 2 and 4 here. Yeah, let's skip that. Matrix multiplication, we already mentioned here, mathmul and dot product. There are also some reduction routines here that return, in this case, that you wanted a Boolean thing. So this is all true if all elements are true. And then any if true if element is true. Then you have max val and min val, which computes the max and minimum value of an array. You can do product here to compute products of an array, sum, same thing. Here you can see product of A here, like this, and that works on an array. And then we have sum of A, max of A, and min of A here as well. You have information functions, so L bound returns the lower index of a field, upper bound, upper field, shape, matrix shape in array, rows and columns. Size is similar to Python. You can return the size of a given matrix in a certain dimension. So I will try to start another. We continue this on Thursday as well, but start a bit input and output. So reading and writing from files is done using the read and write statements, and one row for each, one row of a file for each read and write statement. First parameter determines where to read and write, and if you read from standard input, that is from keyboard, or writing to the terminal, you can use a star on these parameters. And also Fortran automatically converts text in a file to type variable values. So in this case, it's a bit better than Python to interpreter, reading from files and converting to values. Several variables can be read in the same statement using a comma-separated list of variables. But you can also do an implicit loop we showed before. If you have a large number of you want to write in a row, you can use an implicit loop to do that. So this is one option. This will read the variables A, 1, 2, 3, 4 from a file. And the file can contain floating point values separated with spaces. And it will convert it to floating point automatically. But you can also do like this. So for AI, I equals 1 to 8, it will read 8 values of the file. And you can do it the other way around here. You can write and go the other way and write out 8 values to the same line. If you just want to print text that you write in the code, this is a new construct from modern Fortran. You can do print star comma and then the text only, or text and variables. You can skip the formatting star here, just to print out something simple on the screen. So the second parameter in the write statement defines the output format, and if you put a star there, it will use the default format, which is kind of just to dump it in the maximum precision it can. It doesn't look very nice, but it will try to preserve maximum precision. And the formatting parameter is a string describing the output format. It's very similar to Python. You use format codes to define the output. A here is a string with a certain width. So if you want to have spaces in your format, you can use A and then a number. I is an integer with a width of m, and then you have jm.n. That is the width m and the n in decimals. So if you have 6 values you want to print out, you have to do 6i, which is an integer, of 5 spaces, 5 in width. So 6 integer with a width of 5. So here's an example here. I have my variable floating point A here, 1, 2, 3, integer B with 4 values. So I want to print out. So here I want to, the first line here is the header. So I have 3 strings of 8 characters. So here 1, 2, and 3. And then I have 4 strings of 5 in width. So 1, 2, 3, 4. And then I write my table here. So this is just to print the first part of the output. And then here I say I want 3 floating point values with 8 characters of width and 3 decimal points. And then I have 4i5, which is 4 integers of the width of 5. Then I have 2 implicit loops here. I loop over AI and I loop over BI here. And so it's a bit clumsy, but it works. So this will print out 3 values and this will print out 4 values.
So this is concatenated, like the 2 arrays.
It will add a space between them by default. So this is how it outputs it. So you can see here that I have 8 here, and it puts left formats the floating point, and the next one is after 8 characters here, and so on. You could press them together if you increase the width here, but the risk is if there is too much decimals here, it will just print stars or something, so it can't represent it. But this is the way you do formatting output here. You can also see here that I have 5 characters here per column here. I think I stop there and do this dynamic format codes on Thursday. So one problem is that you sometimes you don't have an array of different sizes, and you want to create format codes because there are strings. You need to create a string to adapt to the number of characters. So it's string handling and printing is not the. It's better doing arrays than it is the string manipulation. Okay, so I will stop there.